Hey Ashna,
Hi, Bryant.
how are you?
I'm doing good. How are you been doing? How was your
I've
week?
been doing well too. How was your party?
It was really nice.
Uh-huh.
Yeah, so I'm actually in San Francisco right now. I'm visiting my aunt and my uncle, and so they threw the Diwali party last night, and it was just really wonderful. We had like a bunch of guests, and we had a bunch of yummy food.
Oh wow, that sounds good. That sounds so
Yeah,
fun.
yeah, I
Yeah.
got dressed up in like the traditional cultural wear and wear all the jewelry, so that was really.
Wow. Yeah, dang. Dang. I'm glad you had fun. I'm glad you had fun.
Yeah, it was a really great break from OChem, just like
I know.
locking in
Yeah,
the whole
yeah.
day, and it was just like I just needed a break.
I know, and you've been like doing so much problems because I just checked like the problems and how much they were. There are like so many of them, and then you did like all of them already. That's
Yeah.
a lot of work right there, and you deserve that party.
Oh, thank you.
Yeah. Yeah. So today review session, we could go over like the 10 problems I made for chapter 1, and then
hmm
we could go over the other chapters like 2, 3, 4 problems like the ones you starred. I could go over those concepts with you and create similar
Okay.
ones today. Okay.
Okay, sure, that works. Is there going to be any other students joining the meeting?
Uh, there should be one more, but I'm not sure if they're gonna join today.
Oh,
Right?
okay.
Yeah.
Okay.
Yeah. Okay. Okay. So, for number one, it's asking of those indicated, which would be the shortest carbon to carbon bond. So I'll have you try it, and if you're not sure, let me know, and then I could go over the concept with you, and then we
Okay.
could get the answer from there. Okay.
I want to say D.
D, yes. And why is D here the shortest bond? Correct.
Because like if you go from like a single bond to a double bond to a triple bond, the bond strength increases, therefore the bond length
Mm-hmm.
decreases.
Correct. Yes. Yes. Mm-hmm. Nice. Nice. Okay. Ooh, this one. So this one is convert the following condensed structure to bond line form. Um, yeah, and you could describe to me how you would like convert this condensed structure into bond line form right here.
Okay, hold on, let
Mhm.
me draw it
Yep.
quickly.
Yep. Yep. And then you
Okay.
could like screenshot it, send it to me so that I could see it.
Oh yeah,
That
okay,
would
that
be
works.
easier. Yeah.
Okay,
Do
yeah,
you
that works.
have an iPad as well or a
I
tablet?
do, yeah.
Yeah. Yeah. You could also connect your iPad to the Zoom here, and then you could share your screen, and then I could see it as you were working through it as
Oh,
well. Uh-huh.
okay.
Yeah.
Um, Wait, how do I do that? Like, how do
Uh-huh.
I?
Yeah, do you have Zoom on your iPad?
Oh, because that's why you have the two profiles.
Yeah, the one profile for my computer which I'm talking through, and the other profile for my iPad which I'm sharing my screen through. But the one on the
Oh,
iPad, I disconnect the audio.
oh, okay, that makes sense. I do not have Zoom on my iPad, but I can download it real quick right now.
Uh-huh. Yeah, yeah. That would be best because I could see your thought process and um like real time how you're solving it and give you feedback from there.
And it's the same link from the school,
Yeah, it's the same link.
right?
Right,
Okay, let
right.
me let me add
Mm-hmm.
that in.
Yeah. Yeah. And you could also like annotate over the PDF that I sent you, so then or you could like write it from a separate like file, a separate PDF file.
Yeah, no, that makes
Mhm.
the most sense.
Mhm.
Hold on, let me just
Yep.
send the PDF file to my iPad and then get
Mhm.
the review session loaded up.
Yep. Your exam is tomorrow, Monday?
Yeah, it's tomorrow.
Oh, dang.
But I think I'm feeling ready because it's like MCQs and he says that his long answer it's like what 20 I put a note down. I think it was like 26 MCQs.
Mm-hmm.
And then it was like 3 FRQs, like long answers.
Mm-hmm.
So it was pretty chill and he said like, "Oh, I don't want to do too many long answers because it's going to be really difficult process to grade."
Oh yeah, yeah. Dang. That's good.
I think I am launching it.
Uh-huh.
Um
Yeah. I'm gonna get water really quick. I'll be right back, Ashna.
yeah, sure.
Uh-huh. Yeah.
Recording in progress.
Okay, I'm back and I see your screen.
Okay, awesome. Wait, why is the audio going twice?
Oh yeah, go to Zoom on the app
Uh-huh.
and then click the more button, the three dots, and then disconnect audio.
Oh, okay.
Yeah,
That
there
works.
you go.
Yeah.
Okay.
Here is my. Do I just put that to side? Oh
Yeah, and
wow.
then you could like put it all the way to the side so it's not covering the screen.
Yeah.
Yeah, like
Oh
that.
wow. Okay,
Mhm.
nice.
Yeah. Yeah.
Okay.
Mhm. Mhm.
Oh my God, this is a really hard font structure. Okay.
It is, right.
Yeah.
So before we move on,
Yeah.
look at the very first part, right? You got one of the CH3, CH2s.
Hmm.
Um, and let's see here. CH3, CH2.
And then CH3, CH2, C.
And then the other one you have just a CH3, like the bottom one, the methyl group that you have on the left structure.
Yeah.
That's a CH3. You should add one more carbon coming out of that carbon.
Here, over here.
Yeah, coming out of that carbon right there. Because we don't have a CH3 at the very left. Like, you know how we have two ethyl groups, like from
Hmm.
the parentheses CH3, CH2, and then the subscript 2.
Hmm.
Those two ethyl groups are represented by that right there. Right,
Okay.
right. And then the central carbon, the next carbon, is gonna be that C right there. And you notice how that C has no hydrogens?
Mm-hmm.
So that means that how many bonds two carbons should it have? Or like so if there's no hydrogens right there,
Mm-hmm.
you gotta add how many more bonds to that
Like a
one
triple
carbon?
bond.
Yeah, like a triple bond, but in this case we can't add a triple bond, right? Because you notice how it's already attached to two other carbons by a single bond.
Oh, I see. So it's double.
Yeah, so it's gonna be a double bond, right? So let's erase the right structure. Yep, 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 yep.
Wait, let me try and start again.
Uh-huh. Yeah, yeah. And then you could describe the like what you're like what part of the condensed structure you're drawing.
Okay. So I'll start with this. Like the first CH3, CH2.
Mm-hmm.
So that's there.
Yep.
CH3, CH2. And then the next one I have to draw.
Mm-hmm.
Um, I just thought I could go, that's another CH2. And then that's my ethyl group. So
Oh, right. So for there, right? A thing that you could start off with is the central carbon, right? So ignore the things in the parentheses. So
Mhm.
ignore the CH2, CH2, and look
Mhm.
at the C after that. Highlight that C with any color you want.
This one?
Yeah, yeah, that one right there.
Mhm.
And then highlight that same C on the molecule you just drew on that same color, yellow.
Oh, I see it. But I haven't drawn that yet. So in my thought process, this was
Uh-huh.
CH3, this was
Uh-huh.
CH2, this
Right.
was another CH2, and then this was another CH3.
CH2, CH3, CH2, CH3. Oh, okay, okay. Yeah, I see where that is coming from. The CH3, CH2, right? Because they're in parentheses, that means that they're
They're
substituents,
substituents. Okay.
right? That means that they're gonna have to come off of a central carbon. They can't be connected to each other.
Like the way that you
Okay.
drew it, those two CH3 CH2s are connected to each other.
Oh, I see, I see. Okay,
Right.
okay.
We want them to come off of a central carbon.
Okay, that's my central carbon, and that's the other
Mhm.
carbon there. So we can do a what? C, C, and then an H there, so meaning a double bond.
Yeah, like that, right? But you could draw the ethyl groups coming out like at an angle, so it doesn't go like straight up or down, right? Because if you draw it straight up or down, it looks like one long single bond.
Oh, okay.
Yeah, but you could draw it like an angle and draw the other methyl group coming out. Yeah.
Okay, wait, let me just finish this and then
Yep.
I'll fix my ethyl
Yep.
groups.
Yep. That's good. That's good.
C, C, CH2. C. This one has a triple bond. Oopsies. That should have been longer.
Or like if you like drew that single bond earlier, you could draw the
Yeah.
triple bond coming out of that. So erase the two bonds that you just drew for the triple bond. And then erase that like extension of the bond that you drew, and then draw out the next carbon after the CH2.
Yeah, so because it's like 4 in a row, right? That happen.
Right, like oh, okay, yeah. You
There
could
we
do
go.
that as well. Yep.
So then it's like CH2, C,
Uh-huh.
C, and then I have to make it longer. There's another CH there.
Uh-huh.
Oh, and then we have a C going there,
Uh-huh.
and then triple bond it to an end. Oops. Okay, wait.
Yeah.
I'll
Like
just
that.
yeah.
Yes, that's correct.
And then afterwards we have a C with 3 branches coming out. Oh, okay. C with 1, 2, 3.
Yeah, that's correct. Yeah,
Okay,
nice.
there we go.
It was a little bit difficult because I think the beginning
Yeah.
part, when you're used to seeing a carbon with 0 hydrogens, you think a triple bonded carbon, but
Yeah.
in this case, it's a double bonded carbon.
Yeah, no, this was a difficult condensed structure. It wasn't easy.
Yeah. Nice. Okay.
Draw the resonance structures. Include the arrow pushing arrows. Okay.
Right.
So maybe I'll start by like I know these delocalized they would kind of like they would move around. So
Right.
my first thought process.
Yep. So when you see electrons, and you think of resonance or delocalization, you think of electrons moving. A tip that I have is that if you see a pair of electrons on an atom, right, it could be invisible. You can start with that. So we see a pair of electrons on nitrogen. So you can start with that and move that pair of
Move that
electrons
around.
to make a double bond between the nitrogen and carbon, like that. Right. Okay. So
But
now
then if this one moved, this guy should move away.
to that carbon right there, giving that carbon a pair of electrons. Correct.
Oh, I see. Okay.
Yeah. Okay.
And then that goes there. Delocalize. That one has a plus charge. Oh my god, I messed up.
Right. So that is correct. Like the ring and how there's a double bond between the nitrogen and carbon.
Yeah.
How many electrons are represented in that bond that you just moved to that carbon right there?
What do you sorry, what do
Uh-huh.
you mean?
Yeah, so there's gonna be you know how there's 2 electrons for each bond, like 2 electrons for
Yeah.
single bond. So the second arrow you drew from the bond to that carbon, you're
Mhm.
moving 2 electrons to that carbon, right? So that carbon that you drew with the positive charge will have a pair of electrons,
Oh,
right?
wait, so that would be a negative charge.
Yep, it would be negatively
Yeah.
charged. Positive charge means that it's missing electrons.
Yeah. Okay, wait, let me just
Yep,
redraw the structure
yep,
better.
yep, yep, yep. Mhm.
And then we put that arrow there, so it would be a double. One, 2, 3, 4, 5, 6. There. Negative charge there. That will be a resonance there. Okay.
Yeah, nice. And there's one formal charge missing because we want the overall charge of each resonance structure to be the same, right? The first
Oh,
structure is neutral. We want this structure to also be neutral, right? And you don't have to include that bracket right there because there's already a bracket included for you on like all resonance structures, like on the very left and the
oh,
very
I
right,
see.
right?
Okay.
Yep. And where do you see the missing formal charge? We know that we want it to be neutral. We already have one negative charge, which means that we want to have a positive charge somewhere, like
Mm-hmm.
a full formal charge of +1 to make the overall structure neutral,
It
right?
would be in the nitrogen.
Yep, it would be on the nitrogen because that nitrogen has
Yeah.
4 bonds and 0 lone pair of electrons, making it positively charged.
Positive, yeah.
Nice, nice.
Oh, and then the next one, I would think of. Would it be like if you look at a ring structure, all you do is just keep moving the rings around, like
Yeah, keep moving
clockwise?
the electrons within the ring around.
Yeah.
Right. And then once you can't move it around anymore, you can potentially move it outside of the ring.
Oh, I see. And then you can like change the way the oxygen's bonded.
Yes, yes.
Okay.
Mm-hmm. Okay. And from resonance, when you draw arrows, arrows always represent the movement of electrons. So you always start your arrows from
Negative.
negative charge. And if you see a pair of electrons, I always start with that. So in the second resonance structure, where do you see the pair of electrons?
I would look at this charge over here. The
So that is
yeah.
a pair of electrons. Um, that is a pair of electrons in the form of a bond. But do you see a pair of electrons in the form of like a um, let's say outside a bond? Like it's invisible right now. Like we didn't draw it out, but notice how that carbon that is fully negatively charged, that
Mhm.
carbon has a pair of electrons. So you can
Oh
draw
yeah.
that out if you want, but you don't have to. Or you can start the arrow from that negative charge.
Yeah,
Which
I was planning to do like arrow from the negative charge and then
uh-huh.
the pair of electrons that are in the double bond in the
Uh-huh.
resonance structure, move that out and make it a negative charge.
On the carbon on the bottom. Like
Yes.
yes. Let's do that. Uh-huh. Mhm.
Oh, wait.
Oh, are you Okay. You could draw the arrows from the structure you drew earlier. Like that
Oh,
second
right.
structure you drew, you could draw the arrows from there.
Sorry.
It's okay. It's okay. Uh-huh.
Put that going in there and then that going in there.
Yes. So now there won't be a negative charge on that same carbon anymore because that negative charge went to make a double bond right there. Correct. Nice.
Then from there we go. It's gonna get a negative charge there.
Nice.
And then we have an H there.
Yes, correct. Nice.
And now we can move the because we like moved it to the side, we're gonna move the negative charge out of the resonance structure.
Yeah, out of the ring.
Yeah.
Yeah.
So that can go. Let me change it to a color. I'm gonna put this here. And then
Yes. And then one of the bonds of that double bond is gonna move onto that oxygen right there.
yeah, giving it a negative charge.
Yeah. Giving the oxygen a negative charge.
There we go.
And don't forget the positive charge on the nitrogen as well.
Oops.
Yep. And which one of these, like as an extra problem, is the major resonance contributor?
Like out of all these structures, right? Not just the ones I drew.
Yeah, out of all of these structures, not just the one you drew. And then we'll ask you out of the ones you drew after that.
Oh, okay. Then I think it's gonna be the black one, the one that you drew.
Yes. And what's the reasoning?
Because the negative charge.
We don't want any charge.
There's no charges.
There's no charges, no formal
Yeah.
charges, right? There's no negative charge, there's no formal charge.
Yeah.
No, there's no positive charge, yeah. No formal charge. Nice, okay.
And then out of the one I drew would be this one here.
Yep.
Because the negative charge is on the most electronegative atom.
Yeah, because the negative charge is on the most electronegative atom.
Okay.
On that structure. Yeah. Nice.
Okay.
Okay.
In the lone pair of electrons. In what type of orbital? Oh, 2p.
2p. And what's the reasoning behind that answer?
Okay. Yeah, no, I can't be with one. I'm just blank.
And the lone pair of electrons on the nitrogen and the fellow molecule reside in what type of... Yeah, it is 2p. I just realized that.
Yeah.
So I made it typo in the key, right? Because I was thinking about nitrogen. Nitrogen is sp2, but the pair of electrons is on a 2p orbital, right?
Yeah.
And you know how that's because resonance happens between like adjacent p orbitals, right? There's a p orbital on the carbon next to it as well, right? Like to the left.
Yeah.
Right there. So that pair of electrons can like hop onto that p orbital and then move one of the bonds of the double bond onto the oxygen, right? So here's the thing that I wanted to trick you guys with. imagine that carbonyl was not there. That carbon double bond oxygen was not there. Right? What would be the hybridization of the nitrogen? SP, sp2, or sp3? We'll look at the nitrogen atom, not the pair of electrons.
Oh, okay. If the carbonyl bond was not there.
Yeah, if the carbonyl bond was not there, so you could scribble that out. Yep. And then think about what the hybridization would the nitrogen be. SP, sp2, or sp3?
I mean, won't it still be the same because nitrogen's still very much happy?
Yeah.
So it'd still be 1, 2, 3. It would still be sp2. Sorry.
Oh, so a pair of electrons would also count.
Yeah, so 1 sp 1, 2, 3, 4. So it'd still be sp3.
sp3, yes.
Yeah.
So yeah, it would be sp3 because there's 4 electron groups. Right? So now let's include the carbonyl. Right? So erase that scribble X right there. Now that nitrogen looks sp3, right? Like it still looks like it has 4 electron groups.
4 electron groups.
Right? But now I want you to draw the resonance structure of that. Like starting from the pair of electrons. Like how would you draw the resonance structure of that?
Okay. Oops. Something like that.
And don't forget the double bond between the nitrogen and carbon, and the charge of the nitrogen that has 4 bonds. The positive charge. It will be like that, correct? Okay. Now, how many electron groups does that nitrogen have now? That positively charged nitrogen.
Oh, it's sp. It has 3 groups, so it'd be sp2.
sp2, yes. Right. So now, because it has resonance like that, that nitrogen is going to be sp2 hybridized, not sp3 overall. Right.
Oh, interesting.
Right. And that's because if an atom is sp2 hybridized, how many unhybridized p orbitals would it have? 1 unhybridized p orbital. Right. So that 1 unhybridized p orbital is gonna be the one where the lone pair of electrons on the original structure resides in. Right. So the nitrogen is sp2 hybridized, but the lone pair of electrons will be on a 2p orbital. Right.
On a 2p orbital. Oh, I see.
Yeah.
Okay.
Yeah. If the question was asking like what is the hybridization of the nitrogen, the answer would be sp2, which is what I put because I was thinking about the hybridization of the nitrogen, right? But because that sp2 hybridized nitrogen has 1 unhybridized p orbital, that 1 unhybridized p orbital like holds the pair of electrons for it to do resonance, because resonance happens between unhybridized p orbitals. Like the electrons are gonna hop between adjacent unhybridized p orbitals, like p orbitals who are next to each other. Right.
Okay, I'm just gonna... There. Okay, yeah, that makes sense. But like I think my thinking wasn't as deep as this. My thinking was these pair of, or that 1 lone pair of electrons, unless it's hydrogen, it's always on a 2p.
Unless it's on a hydrogen, it's always on a 2p.
Yeah, like the lone pair of electrons. So if they ask me for oxygen or if they ask me for nitrogen, it's not hydrogen, so therefore it has to be 2p.
2p. Yeah, did Farhat say that, or did like a different professor say that?
That was like the TA.
Oh, TA said that. Like,
yeah, he just made a general, because we had like our quiz was, the most recent quiz we did was all on hybridization. So yeah, he just kind of said that general rule before we started the quiz.
Oh, right. Let me check one of his practice rounds, because I think he said that one of the pair of electrons resides in the sp3 orbital. But let me make sure. Let me double check it really quick.
Okay. Yeah. But like if they just clarifying, like if they have a question, instead of saying where does a lone pair of electrons stay, it would be like what is the resonance of this molecule, do I have to put like what is the resonance of the nitrogen in this molecule? Would the answer be wrong if I say sp3?
sp3. Yes, if you're asking for the hybridization of nitrogen, it wouldn't be sp3, right? It wouldn't be sp3.
It would be sp2 because of the resonance.
Yeah, because of the resonance. If that carbonyl was not there, like destroying all resonance structures, then the nitrogen would be sp3, right? Because there's no
Wow.
resonance, right? That's a tricky one. That's a tricky
Yeah.
one. 6. Let's see here. 15. Yeah. So on number 15 of chapter 1, practice problem, that's why I created a similar problem. It asks for the lone pair of electrons on nitrogen in the following molecule resides in what type of orbital. That nitrogen pair of electrons cannot do resonance, right? Which is why it's gonna be in like a hybridized orbital, like sp2 in that structure.
Oh, I see.
Right,
Okay.
right, yeah. So I just made it based off his practice worksheet.
Okay.
Right. Okay. Nice. Okay. Ooh.
Oh.
A lot of counting for this one.
Yeah. You're really challenging me with these chapter 1
Yeah, I
questions.
know.
Yeah.
And then I didn't create the multiple choice as well. So I like have you actually like count it instead of like choosing the closest one, you know?
Mhm.
Yeah.
I don't even know where to start.
So
Okay.
for this one,
Yeah.
molecular formula, it usually starts with carbons, right? So
Yeah.
let's start with counting all the carbons, right? And if you have a highlighting tool for that, you could use that, or you could just like highlight each point that you see on the structure.
So, like, is it
The
okay if I
carbon.
give you the condensed molecular formula or no? Is
Yeah,
that what?
that is what it's asking for, the
Oh,
condensed
the
molecular
condensed.
formula.
Oh,
Yeah,
I see. Okay.
like
Okay. Okay.
CHON, like how many of each?
Okay. Okay. I got this.
Uh-huh. Wait, were you thinking like you were gonna draw like the Lewis structure or something like that, or like Kikuli
Yeah,
structure?
like the what is the other one that we did in the quiz? So we did like bond line,
Uh-huh.
and then we did the
Kikuli.
yeah, Kikuli structure, and then there was another one. There was another structure.
Lewis.
No, it was like it was not the condensed
Uh-huh.
molecular formula, but it was kind of like a molecular formula. But the way they
Uh-huh.
expressed it was like it's like how you draw it, if that makes sense.
Right. I see. Like in a single line.
Yeah, in a single line.
I see. And I think it's not condensed formula because like it includes like the double bonds explicitly and the triple bonds explicitly.
Yeah,
Right?
sometimes. Like what
Yeah.
we were working from the previous problem, where
Mm-hmm.
we had that like line structure, and then we had to draw the bond line from that.
Mm-hmm.
That
Oh, I see.
that
Like,
was the formula, yeah.
right. I see. Bond line
Yeah.
structure. Yeah. Like this right here is bond line structure right
All
now.
that structure, yeah.
Yeah. Yeah, bond line structure is gonna be the easiest to read out of all of those, like Kikuli condensed formula, because it's much more clean. All the hydrogens are invisible. Right.
I know, right? Yeah.
Yeah. except the hydrogens on aldehyde and alcohol
Oh, yeah.
and nitrogen. I mean.
Those are all like implied.
Yeah, on the carbons, they're all implied, except aldehyde.
Okay.
Okay. Let's see.
I think that should be it.
C20, H32. Uh-huh.
And then I just do like 1N. Or is it O first?
N-O. I think, yeah, I think if you write any answer,
O-N?
it wouldn't work. I think it would be O-N, yeah. Like usually I see O-N.
Yeah.
Yeah, 32. Okay.
Yeah, am I
Okay.
missing a hydrogen?
You added one extra hydrogen, right?
Okay, let me try and find it.
Uh-huh. I'll give you a hint. The hydrogens that you counted out so far, right? There should be one formal charge of +1, right? But because there's no positive charge, like look at the, let's say, nitrogen, right? It's neutral. So if it's neutral, how many bonds would
Oh,
nitrogen want to be neutral?
3 in 1 lone pair.
Yeah, 3 and 1 lone pair.
Yeah.
Right. If you added that hydrogen there, what would be the formal charge of nitrogen?
It would be positive.
Positive, right? And
Yeah.
like that hydrogen can't be implied. Like if there was a hydrogen there on nitrogen,
Oh, I see.
it would have to be drawn out explicitly, right?
Okay.
Yeah.
Oh, so close.
So close.
So it was 31?
Yeah,
So-
it's 31. Yeah. But Fahrenheit's exams would be multiple choice, so you'll be able to like find the one closest to that right there.
Yeah.
Okay. Nice. Nice.
Draw the Lewis structure. Okay, cool.
Did he also ask you to draw Lewis structures for the quiz, the previous quiz?
No, there's no
No.
structures, but like
Oh, okay.
kind of have to know it. Like maybe he might say draw the bond line structure of
Yeah,
this.
draw the bond line structure instead. Like the Lewis structure is way too much. It's way too messy. Yeah.
Okay.
Yeah. It does show up on the practice exam though. This is where like I made it similar to the practice problem. But I'll just ask you like how you would draw the Lewis structure instead of drawing it out because it's messy.
Oh, maybe. Oops.
You figured that out, like the geometry of triple
Yeah.
bonds, linear straight. I always made that mistake. Like I always make a bend.
You're like, oops.
Yeah.
Is it too long? No, it should be fine.
No, yeah, that's good. Nice. And B, boron, what formal charge would it have if it just has 3 bonds?
Neutral.
Neutral.
Yeah.
Nice. Yep. So that's the bond line structure of that structure. How would you draw the Lewis structure? Like what does each bond represent?
Okay, so then nitrogen doesn't have any H's because it's neutral. And then carbon won't have any H's either because it's making a triple bond and it's making one bond with boron, so it's like full. And then I would draw like here I would add like my 2 H's. And then over here like I would add my I would add like my 3 hydrogens, and then over here I would add my 2 hydrogens, and then over here I'd add my 3 hydrogens.
Yes.
Sure.
Correct. You would have to actually draw out all the invisible hydrogens if there are any, all the invisible implied pair of electrons, which we do see one on nitrogen, right? There's an invisible pair of electrons there as well, and each bond represents 2 electrons. Instead of drawing, well, for Fahrenheit's like answer key, like he replaced each bond with 2 electrons. Right. Yeah. So and you would have to like draw out the carbons as well. Like each point in the bond line structure represents a carbon. You would have to write out a C for the Lewis structure as well. Nice. Okay.
Okay.
More resonance.
Okay, I think I can be less shaky with this. Oops.
There's actually 2 ways you could start this resonance, but if you start with either way, you get the same answers. Yeah.
Ooh, do you guys want to try Kahoot after this? After we try the 10 problems of chapter 1, Kahoot on
Yeah,
chapter
sure.
2 and chapter 3?
Yeah, sure.
Yeah, let's do that. Okay.
Mm.
Yeah. Before Kahoot, I want to give a quick overview of Newman projections and chair conformations.
Okay.
Okay, then another big topic would be free radical halogenation.
Yeah. Let's just do this.
So for this one right here, you can basically do what you just did, right?
Mhm.
Where you put a pair of electrons on that carbon, giving that carbon a negative charge.
Mhm.
The other carbon lost a bond, so that carbon would be positively charged, right? The one on the bottom, right
Yeah.
there, right? But that right there is very unstable because there's way too many formal charges. Like there's 3 formal charges right there.
Yeah.
Right. So instead of doing that, another way that we could do it is like, you know, the positive charge on the very top, the carbocation, there is a void there. It's missing electrons, right? So you can move that double bond instead of moving it directly onto the carbon. You can make a double bond between the carbocation, which is the carbon with the positive charge, and the carbon to the left. Right. So draw an arrow of, instead of going on the carbon, you make another
Carbon?
double bond. You make a double bond.
Oh,
So you
okay.
make an arrow to the bond.
I was kind of thinking of that, but I'm like, doesn't it have to move to the atom first and then move from the atom to the
It doesn't have to do that. It doesn't have to do that. Some
Oh, I
cases, like
see.
we want to do that with like negative charges, but in this case,
Yeah.
it's a positive charge. We want to fill it up with a bond like that.
Dude, that's what I was trying to do, but I didn't want to like skip a step.
Right. Yeah.
Okay.
Like the way that you did it isn't wrong. It's correct, right? But that's why I give you the arrows, resonance arrows, so then you're restricted to the major ones. Yeah.
Okay.
Nice.
So then this one loses its negative charge. And then does this one become positive though?
Yeah, it becomes positively charged. Yeah. Isopropyl is still there. Nice.
Okay, and then this one, it's like the same thing.
I
would
You could
just
draw the
yeah, the arrow. Like I would just draw it like that.
Yeah, just like that, right? Fill in that void, that empty space with no electrons with that double bond, but then you're creating another void. You're creating another carbon with a positive charge somewhere.
Okay, so then it just kind of repeats itself.
Right. Yeah. The last example was about like carb anion, carbon with a negative charge and a pair of electrons. Right. This one is with the carbocation, a carbon with a
Carbocation.
positive charge, missing electrons.
And then oh, it just repeats. Oops, wait. Okay, I think for the last one, I can't just like move it around again because I've given everyone a positive charge.
So you can move it one more time, because one carbon that doesn't have like positive charge where it hasn't been yet, and there's one more unique structure for if you move one more double bond.
It has to be like at the bottom.
Yeah.
Okay.
Right. There hasn't been a positive charge at the bottom yet. And you would create that by moving it there. Yeah, moving that double bond there. Yeah, and then isopropyl. Yeah, there you go.
There.
Nice. Okay. Have you learned about carbocation stability yet?
I don't think so, not yet.
Okay. We won't worry about that here.
Okay.
Okay.
Oh, 5 structural isomers of 6. Okay, I'm good at this.
Yeah, let's go.
We'll start with the basic one. 1, 2, 3. Okay. That's one.
Nice.
And then I'll just move a little methyl group here.
Nice. One, 2, 3, 4, 5, 6, 3, 6, 9, 11, 13. What, 11, 13, 14. Oh yeah. That works too. Yeah. Nice. 1, 2, 3, 4, 5, 6. 3, 6, 9. 11, 14, 3, 6, 9, 12. Oh shoot, okay. So that one I didn't include. There should be 6 then. that one I didn't, yeah, I didn't include that one.
Okay.
Which is
Okay,
good.
I'll try and
Yeah.
think of the 6th one.
Yeah. It's good.
Wait, why is this? No.
Nice.
Okay, 1, 2, 3, 4. 1, 2, 3. I feel like this looks so ugly, that structure, but it makes sense.
1, 2,
5, 6.
3, 4. Yeah, that works.
But is it the same? Hold on. 1, 2.
Oh wait. 1, 2, 3, 4, 5. Oh wait, actually no. There's something missing. there.
Okay.
1, 2, 3, 4, 5, 6. Wait. What? 1, 2, 3, 4, 5. Oh yeah, that's the same as number 2.
Yeah, that's
number
what I
5 is the
thought.
same as number 2. Let's try something with 4 carbons long as the longest carbon chain. 4 carbons long as the longest.
Oh, I see. Okay, wait.
Uh-huh.
I can move it around. 1, 2, 3, 4.
And you know how you added an ethyl group on carbon 4?
You mean on carbon 2?
I mean structure 4
Yeah.
on carbon 3 or
Yeah.
2. Instead of adding an ethyl group, You could add
Oh, two methyls.
yeah,
Yeah,
yeah.
okay, there we go.
Yeah.
Yeah, okay, there we go.
Yeah.
I can do something like this.
That's one of it.
6, and I can do 1, 2, 3, 4.
Yeah, like that.
There we go.
Right. Nice. Okay. Yeah. Let's go.
How many hydrogen atoms? Oh my god. Okay.
Hydrogen atoms,
Uh,
yeah. This one, when I made the
the
problem,
MCQs, I would actually like crash out. Like it
you
would
crash
take so
out.
much time.
I know, like just
It's
counting
on
the
the
hydrogens.
test.
I know. Like I will skip this problem like, and go back to it at the end because I'm like
Yeah.
this is way too much time. Like I will do the ones that I'm confident with the most, so then like I get maximize the points on the
Yeah.
exam, and then come back to the ones that would take a long time.
Longest
Like,
time, yeah.
I got
Because you can't guess your way through these. Like
yeah.
even if you want to, you're gonna get it wrong. You have
Yeah. Right. Uh-huh. Like when I made this problem, like and I recounted it again, I got like different numbers 3 different times, and I got so annoyed. I was
no.
frustrated. I was like, oh shoot.
Oh.
So hopefully the one that you get matches the one with what I got. Like I
Okay.
might have a typo on mine.
Okay.
Yeah.
I'll be really serious and count.
Yeah. Three. Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
12,
12,
13.
13.
14, 15.
14, 15.
16.
16.
17.
That has no hydrogens.
Wait, why? Oh, because of the double one.
Yeah.
Wait, so we're down to 16? 17. 18, 19, 20, 22, 23, 30, 31, 32.
Okay.
Okay.
There's one more sneaky one hiding from you somewhere.
Okay.
Somewhere in the ring.
Are you sure?
Yeah, look at the benzene ring.
Yeah.
Look at the top right. I mean the right. That one right there.
Here?
Yeah, that one. Yeah, because that carbon only has 3 bonds to carbon and 1 invisible bond to hydrogen. That one right there. Right, the other carbons in the benzene are already
Right.
like
Already
bonded to
bonded.
4 different carbons.
Oh, I see. Because 1, 2, 3. But then why is there no? Oh, because of the double bond?
Yeah.
Yeah, okay. So it's 32 in total.
33.
33? Okay,
Yeah.
33. Yeah, I know that's tough.
Yeah. At first I got 36 when I counted it.
Yeah.
And then I got 32. And I did it again, I got 33. And then I did it again like 2 more times just to make sure it was 33.
Okay, wow.
I know. I tricked myself. Oh my gosh.
Yeah.
Okay.
Okay.
Yes, last one for chapter 1.
Oh, wow, okay. Okay. I feel like in chapter 1, resonance was like my weakest, but I'm glad that I did all the problems on resonance.
Yeah, on the discussion manual, there's a lot of practice for sure.
Yeah.
But have you encountered any typos? Because there could be some typos in the discussion manual.
In the discussion manual? So I was really, my first quiz ever, I was a little bit foolish because I thought Levens and Fahrenheit had the same like discussion quizzes. Like that's what people were like talking like in my friend group. And the discussion manual was really like they had like a lot of topics for quiz 1, but Levens said that there's going to be no resonance on the quiz. It's like, okay, I don't think there's going to be that much resonance. So I didn't practice as much resonance for chapter 1. and I practice more of the other topics, like the drawing from like the Kaluki structures, bond line structures, condensed
Nomenclature, yeah.
nomenclature. So I did a lot of that, and I didn't do as much resonance.
Uh-huh.
When I went to the quiz, half of Fairhout's quiz was resonance.
Residents. Oh no.
So I was like, oh snap, like I did not practice
Mhm.
enough resonance.
Yeah.
Yeah, but
It's
it's okay.
different, yeah. It's okay. You learn. Now you know like Levens and Ferha will teach different things at different paces. Yeah.
Exactly, yeah.
Uh-huh. Have you heard of Levens vocab section? Like,
No.
oh, okay. That's like, yeah. You gotta be very like careful and pay attention to like how she explains things for that section. Mhm. Okay.
Oh wow.
Nice. I like how you started with the negative charge, right? Because resonance, we start the arrows with the negative charge, and you start with the former charge of -1 to create a double bond there. Nice. That would break the octet rule if you don't do anything else. So we would have to do something else.
You'd have to move that.
Yeah. We would have to move that. Yeah. Right there.
Giving that also a negative charge.
Yes.
Yeah, okay.
So that's doing it one by one, right? Later on when you learn about reactions and mechanisms, that double bond, like it could go like all the way across to the other side of the molecule if you wanted to, like draw it like straight across to get the other end of the resonance structure right away, right?
Wow.
But we want to do it one by one because we're just getting used to like resonance here. Wait, Amanda, are you familiar with Newman projections and chair conformations?
Not chair conformations.
Not chair conformations, okay, but Newman projections, you know how to see and read it, like Gauss, anti, the difference in stability and energy between those conformations, like staggered, eclipsed, torsional strain.
Not much.
Not much. Okay. I'll go over that. I'll go over them after this.
Sorry.
Yeah, it's okay.
Okay, I think I got it.
Right, and then don't forget the double bonds in the
There we go.
That is very important because if the double bonds were not there, then that'll be it. that'll stop the resonance structures, right?
No.
I know.
And then I would move this from the negative to over here. But then someone on the resonance structure they have to move, otherwise octet could be broken.
Yeah. The octet rule of the carbon in that ring would be broken, so you would move that double bond there to create a negative charge on that carbon.
Yeah.
Nice.
Wait, do I have to always? I'm gonna see if I can just
Copy and paste.
Yeah.
Or you could just draw out the squibbly sign to show the fragment, and just draw out that ring and show where the negative charge would be at, and everything else would be the same. Yeah.
Oops.
You found out that that double bond is not there because it moved on to that carbon, giving that carbon a negative charge. Yeah. Okay.
And then we just have a double bond here, making that no, that just stays neutral.
Neutral, right? Yeah. Nice.
And then what happens next? Negative charge moves from like here to like down there. And then that one moves away.
To
Oh wait. It can move to the nitrogen.
It can move to the nitrogen. It can make a double bond there, right? But if it makes a double bond right there to the nitrogen,
because the nitrogen has a hydrogen. That's a positive charge.
Right. It still can, right? Like we can make a double bond there between the carbon and nitrogen. We would just have to move the right double bond to that carbon, given that carbon a negative charge, right? But
Yeah.
that will skip to the very last resonance structure, and we don't want to do that. There's one more resonance structure in between that point, right? So start with the negative charge again on that carbon.
Okay. So I would just negative charge. I would move it.
Oh, start with the arrow from the previous resonance structure, and then this resonance
Oh, right.
structure that you're drawing right now is the new one.
Sorry. Okay, so this one goes in, this one goes out.
Onto the. Oh, right. So this one might be a little bit tricky to see. Draw out the right part of the structure for that one, like the whole thing with the nitrogen.
Oh, I see. Okay.
And isopropyl. Yeah. There you go. Now you can move that double bond onto that carbon right there, next to the nitrogen.
Okay.
So it will still be on the ring like that. Yes.
So then that one has a negative charge.
Yep.
And then this bond goes there.
Now there's one more resonance structure from that point.
Okay, and then let me draw the other one. The negative charge goes there, and I'm gonna move this there.
Yep. Onto that carbon right there on the very right.
Yeah.
So we don't want to jump carbons. It would be on the carbon inside, like that one that is still bonded to the double bond. Yep. That is the part of the double bond, like that. Yeah.
Here. Okay.
Right. Okay. And on an exam, don't draw the negative charge and bond like that. On that structure. Yeah. But put the negative charge on top of the bond or below the bond. Right. Or around, like nearby that bond, that carbon.
This carbon here, right?
Yeah. Right. Okay.
Okay, there you go. There we go.
Yep. Nice. And don't forget the positive charges for all of the nitrogens, because the nitrogens would be positive charged throughout everything.
Wait, give me 1 second. Let me just charge my iPad before it dies.
Yeah.
Oh, did it die?
Oh.
It's charging. Okay.
Yes.
Wait, just ignore that. Okay, there we go.
Yeah. Are you sharing your screen still?
Yeah. Can you see it or no?
No, not anymore. No.
Okay, sorry. Give me 1 second. Share screen. Oh, that's the key.
Now we can see it.
Yep.
Yep.
So that's my final structure there.
Yes, and don't forget the positive one charge for all the nitrogen atoms and all these resonance structures. Because all the nitrogen has 4 bonds and 0 pairs of electrons, making it positive charge. Right.
Everywhere.
Everywhere, yeah. All of the resonance structures. And that maintains the overall charge of every resonance structure, which should be -1. Overall charge should be -1.
Oh, I
Wait,
see. Right.
is it?
Wait.
Oh, it's neutral. It should be neutral.
Neutral, yeah,
It should be
yeah.
neutral.
Because it's like there's negative charge there too.
Wait a minute. Oh, wait, erase the positive charge on the first two because we already have a positive charge there on nitrogen.
Oh, oops.
Okay, there you go. Now everything is neutral. Now everything is neutral.
There
Yeah, positive, negative, positive, negative. Yeah.
Okay, awesome.
Nice, nice. Okay, let's do. Do you guys want to do Newman projections or cyclohexanes and chair conformations next?
Cyclohexane.
Cyclohexanes. Okay, okay. Let's do that. Okay, you can stop sharing your screen, Ashna, and I'll start sharing mine. Okay. Okay. Let's do cyclohexanes and axial, equatorial, more stable conformer, less stable conformer, 1-3 diaxial strain. Okay. Okay. So cycloalkanes, they're gonna be rings, right? And here are the different ones that you can see: cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, and cyclooctane, right? Cycloheptane, the one with the 7-membered one, is really hard to draw for me. Right, but I'll try drawing it. Let's see. So this is cycloheptane, this is cyclohexane, and then this is cyclo. Oh, did it? Let me share my screen again. Okay. Okay. So this is cycloheptane with a 7-membered ring, I think, hopefully. 1, 2, no, that's 6. That 1, 2, 3, 4, 5, 6, 7, and a cyclooctane. Okay. Now we know that each of these carbons are sp3 hybridized because they have 4 electron groups. That is not going to do resonance anywhere, right? And do you guys remember the geometry and preferred bond angle of sp3 atoms?
Was it tetrahedral?
Yeah, it's going to be tetrahedral. And what would be the preferred bond angle for tetrahedral sp3 carbons?
109.5.
Yep, 109.5 degrees. But in this like equilateral triangle, so we'll do a little bit of geometry here. What would be the bond angle that this carbon is forced to be in right here?
60.
Yep, 60. The preferred bond angle is 109.5, but this carbon here in this cyclopropane or this triangle is going to be 60 degrees, which is far away from 109.5. So that would introduce something called bond angle strain. Bond angle strain. You might see torsional strain, right? Or torsional strain. Which is a type of ring strain. Okay. Now let's look at this cyclobutane right here. What bond angle is this carbon forced to be in this square, in this cyclobutane?
90 degrees.
90 degrees, right? And this would also have bond angle strain or torsional strain, but not as much as the cyclopropane, right? Because the difference between 90 and 109.5 is smaller than the difference between 60 and 109.5, right? Like 90 is closer to 109.5. So it has a smaller ring strain, smaller bond angle strain. Okay. Now, let's see here. The cyclopentane would be around 108 degrees. The cyclohexane right here, that is like drawn in this form, is going to be around 120 degrees.
and then the other ones would be bigger and bigger numbers, right? So the most stable rings that you will have are 5 to 6 members rings, but this 6-member ring here is like far away from 109.5 as well. But in nature, it doesn't usually exist in this form, right? It usually puckers and twists itself into something called chair conformation, which would look like this, which is still 6 carbons long, right? 1, 2, 3, 4, 5, 6. But the reason why it is going to be in this form is because it allows the bond angle, right, for these sp3 carbons to be closer to the preferred bond angle of 109.5 degrees, like that, right? That's one chair conformation. We can flip this one chair conformation to a different version, which is going to be this right here, right? They're going to represent the same molecule, but it's just going to be the way that they twist itself into like the structure would be different. Like the axial and equatorial bonds would be different for each carbon, right? Okay. Now, I need to make sure that I show like the right rotation for this, because that's the hardest part. 1, 2, let's see, rotate clockwise from here. Okay. Okay. Any questions on this so far?
No.
Okay. No? Okay. That's good. Okay. So I'm gonna draw out one of the chair conformations and describe to you guys difference between axial and equatorial bonds. So let's start with axial bonds, which is the easier one, because it's gonna go either only up or down. It can only go up or down, like straight up or straight down, right? And it's always gonna be fixed. Like the way that I'm gonna draw it here is always gonna be true for all problems, right? I like starting at the top left corner, which is this carbon right here, and that's always gonna go up. If you look at the next carbon, which is like this or this, it's going to be opposite of up. So it's going to alternate between up, and then the next carbon would be down, the next carbon would be up, the next carbon would be down, next carbon would be up, the next carbon would be down. So it alternates between up, down, up, down, up, down, like that, right? So that would be the axial bonds for chair conformations. It's always going to be like this. Any questions on that? Okay. That's good. Now, let's move on to equatorial bonds, which is the harder one to draw because it goes at an angle, right? It's not going to go directly up or directly down. Equatorial bonds would be in opposite direction as axial bonds. So if we look at this carbon over here, we see that the axial bond is going up. That means that the equatorial bond has to go down, which is opposite to up, right? So let's say like this is the line right here, right? So it's not gonna go up. It's not gonna go up right there because that's up, right? It's gonna go down here, 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 or there, like that, right? But to tell what direction the equatorial bond is gonna go to, right? It's going to be parallel to the next two bonds. So what that means is that if you look at this carbon here, which is the carbon that we're interested in, ignore the bonds directly touching it. Like these are the bonds directly touching it. So I'm gonna put an X there and X there because we're gonna ignore those bonds right there. Then we look at the next set of bonds, which is gonna be this bond, the one I'm highlighting, and that bond. Those are the next like set of bonds right there. The equatorial bond is going to be parallel to those bonds right there in the same direction as those bonds going down like that, right? It's not going to go here, which is still parallel to those bonds, right? Because this right here is going up. Like if you draw that bond, it's going up and we don't want that bond going up, right? So this is going to be the equatorial bond going down like that, which is parallel to this bond and that bond. Okay. Any questions on that, on how I got to this bond, equatorial bond? Okay. Now let's do the same for this one. This carbon here has an axial bond that's going down. So the equatorial bond has to go up. So to determine the direction of that, I'm going to ignore the first set of bonds, which is that bond and that bond, that is directly touching this carbon that we're interested in. And then we look at the next set of bonds, which is this bond or that bond, right? They're going to be the same direction. So we're going to draw our equatorial bond going up in that same direction like that. Same direction as this next set of bonds right there. Okay. So what will remain true is that the axial bond and equatorial bond will always be opposite to each other. Axial is up, equatorial is down. Axial is down here, equatorial is up here. Okay. So the next carbon, axial is up, equatorial would be down, parallel to the next set of bonds right here, where we ignore the first set of bonds, right? Okay. Okay. So we could do the same. Yeah.
Sorry, I don't know if this is jumping a couple of steps, but how do you know if they're cis or trans?
Oh, how do you know if they're cis or trans? I think you're thinking of decalenes, right?
Mm-hmm.
Which is gonna have like a fused benzene ring. Or like if you just have a regular structure like this, you know that the two groups are gonna be cis if they're both wedges or both dashes. So that's cis right there. And trans would be like one would be wedge and one would be dash, right?
Mm-hmm.
Like cis, meaning that the two groups are gonna face on the same side, like either both wedges in this case or both dashes like this. Trans would be like one would be wedge, one would be dash, like that, on opposite direction, right?
But what about if it's in the chair conformer?
So if it's in a chair conformer, for it to be cis, they have to go on the same direction. So let's say like we already have all the axial bonds drawn out. This is the isopropyl group, and then we have a methyl group right here. Those will be cis to each other because they're both facing up.
Oh, okay.
Up like that, right? Okay. Trans would be like if this is the isopropyl group, and then this would be the methyl group going down like that. Right? It doesn't have to be axial bonds. It could be axial and equatorial, right? It doesn't matter. The only thing that matters for cis and trans is the direction. So if we had an isopropyl group here going up, we could have a methyl group here going down in the equatorial position. That's still trans because the direction is still opposite, right? So cis and trans doesn't matter about axial or equatorial. It just matters about the direction, the difference in direction.
Yeah. So like let's say there's like an isopropyl group in the same axial position, but then you move it to the equatorial position. That's kind of like going the other equatorial position.
This one right here?
Up, yeah. That's gonna be cis.
Yeah, that's gonna be cis.
Oh,
this is gonna be cis, right? Because they're both facing up.
Okay.
Yeah. Okay. Nice. Okay. And you can only cause like a chair conformation cis or trans if it has exactly two substituents. Like if it has more than two substituents, you can't say cis or trans anymore. It has like three or more, you can't say cis or trans. If it only has one substituent, you can't say cis or trans. It has to have exactly two substituents for you to call it cis or trans.
And they don't have to be like matching substituents, right?
Yeah, they don't have to be matching substituents, right? They can, but they don't have to be. Right. Okay. So if you do the same for all the other carbons and you draw out the equatorial bonds, which is going to be parallel to the next set of bonds, you would get these right here. To make sure you have the right answer, there's two things you could look out for. The equatorial bonds would be opposite direction to the axial bond, right? It's like if axial bond is up, equatorial bond has to go down. If the axial bond is down, equatorial bond has to go up. Another way that you could make sure that you have like the right structures is that the equatorial bonds would have to face away from the equator or the system, which is this cyclohexane structure right there, right? Like all of these equatorial bonds here are facing away. They're not like running like inside of the system like that, or the equator like that. They're facing away from the equator for the equatorial bonds, right? Okay, now this is the tricky part here, trying to convert this one chair conformation to this other chair conformation with the exact same number, right? So How do you guys want to number this? It doesn't matter how you number it. The thing that matters a lot is like how you flip it, right? You gotta stay consistent. So where do you guys want to number our number one atom here? It doesn't matter.
Like bottom left.
Bottom left, right here.
Yeah.
Okay, 1. And where do you want your number 2 atom to be? Here
like
or
you can do
here?
it- Yeah, we can just do it like clockwise.
Clockwise? Okay, so let's do it here. 2, 3, 4, 5, and 6. Okay. Now, if we flip it to this chart confirmation, the numbers would be like in the same carbon still, right? But those same carbons are gonna be in different locations now in this chart confirmation, right? So, Ashton, do you know, or Amanda, do you know where number 1 would be in this chair flip now? If this is number 1 here on this chart confirmation?
Be where number 2 is currently.
Yes, yes. Where number 2 is currently, that's where number 1 is, right? But that doesn't mean that like this carbon here was this carbon, right? There are two different carbons. We're just flipping the molecule to like flip this carbon here, number 1, to up here, right? Like that's still the same carbon right there. We're just flipping the location.
So are we like what do you mean by flipping? Because are you like squeezing it up, like, or are you flipping it like that way, or
Like it's
like
rotating, I think 60 degrees.
yeah, rotated 60 degrees.
Okay.
Where you know how this part is like facing down and this part is facing up?
Yeah.
Now this part is facing up, this part is facing down. Right? Like
Okay.
we're like rotating each like 160 degrees to make it like pucker into that conformation, basically.
Okay.
Right.
And so is it kind of like the Newman projections where they keep rotating 60 degrees to like different conformations?
And they're gonna keep rotating in between these two chair conformations like that.
Oh, I
Right.
see.
And in some molecules, one conformation would be more stable, which means that they would have less energy, right? But that's for some molecules, right? Okay. Now, to draw the axial and equatorial bonds, I like to start with the axial bonds. I start with the top left corner, start up, and then the next set of bonds would be alternating, like up, down, up, down, up, down, like that. Equatorial bonds would be opposite to the axial bonds, parallel to the next set of bonds, which would be like this. And now, here's the most important thing, right? If you look at, let's say, atom 1, what direction is the axial bond pointing towards? Up or down?
Down.
Down, right. Let's look at the number 1 atom on the next chart confirmation. What direction is the axial bond pointing towards?
Up.
Up, right. The direction of each axial and equatorial bond would flip, would be changed, right? If you look at the equatorial bond on carbon 1, that's facing up. If you look at the equatorial bond on carbon 1 on the other chair conformation, that's facing down, like that. So the direction of each axial and equatorial bond would be flipped for the two different chair conformations, like that. Okay. Okay. Now, let me give you guys that same structure I gave you guys. That is gonna be, let's say, cis, like this. And it doesn't matter how we number it because we're not doing nomenclature here, right? I'm just gonna say that's 1, 2, 3, 4, 5, 6. And then let's copy and paste like the chair conformations over here. And draw the two different chair conformations of this structure here, of this cis cyclohexane here. Okay. So let's look at number 1, which is this right here. If you see a wedge, right? Let me make this dash so I could explain the difference between wedge and dash. What does that mean? What does this wedge mean to you guys?
It's coming out of the paper.
Yep, it's coming out of the paper towards you, right? So it's gonna go up, like towards you. So now, what does a dash mean to you?
It's going away.
It's going away
Paper.
into the paper, so it's going down away from you, right? Now think of wedges as up, dashes as down, right? So wedge up, going up towards you, away, like up into the paper towards you, or dash is into the paper away from you, down, like that. Okay. So now we see this isopropyl group here is a wedge, which is gonna go up. Now if we look at carbon 1 over here, what bond is going up? Axial or equatorial? For this chair conformation here on carbon 1.
Equatorial.
Equatorial. We see axial is going down, equatorial is going up. So our isopropyl group would be on the equatorial bond, like that. Right. So this carbon here is sp3 carbon, meaning that it will have 2 flat bonds, which we already see here. Those are the 2 flat bonds, 1 wedge bond and 1 dash bond. There is 1 dash bond here, but that is invisible because it's to a hydrogen, right? And because the hydrogen is going down because it's a dash, that should be the hydrogen right there. But we don't have to draw that out explicitly. It's gonna be implied, like how it is implied for bond line structures. So we could erase that right there. But we know that that is still there, right? But it's just invisible. Like this axial bond going down is there, bonded to a hydrogen. Okay. Now let's look at carbon 2. Where would the methyl group be on carbon 2? Axial or equatorial?
Equatorial?
Yep. Because methyl here is a dash, meaning that it's going to go down. And if we look at carbon 2, we ask ourselves, what bond is going down? Axial or equatorial? And in this case, at carbon 2, the bond that's going down is equatorial. Right? So that's why there is an invisible hydrogen that is a wedge on carbon 2, which is going up. So that's going to be the invisible hydrogen right there, which we can erase because we know it's there. And then everything else we can erase because everything else is attached to hydrogens. Every other bond is attached to hydrogen, like that, right? So we see an isopropyl group here on 1 that is equatorial, and a methyl group here on 2, which is also equatorial, right? Okay. Now, if we do a chair flip, the direction will always be the same. Like wedge will always be up, dash will always be down. You cannot change that, right? But what can change between chair flips is axial and equatorial. Because now let's look at carbon 1, which is the isopropyl. What's going up now on this chair conformation? Axial or equatorial?
Axial.
Axial, right. So our isopropyl group is going to be right there. Hydrogen is invisible. Now on carbon 2, what's going down? Axial or equatorial?
Axial.
Axial as well, right? So that's going to be our methyl group right there. I'm going to erase every other bond because that's going to be in hydrogens. So now we notice that the equatorial isopropyl group turned into an axial isopropyl group in the chair flip. The equatorial methyl group turned into the x-axial methyl group, right? So every time you do a chair flip, axial will always convert into equatorial with that group, or equatorial will always turn into axial with that group. They will always flip whenever you do a chair flip, right? But what will not flip or what will not change is the direction. Like they will always stay up or they will always stay down, like that. Okay. Now, what is the bulkiest group here? Isopropyl or methyl? What is the bigger group?
Isopropyl.
Isopropyl, right? So now I'm going to highlight the isopropyl group because this is what we're going to be interested in when we determine the stability difference between the 2 conformations, like what's more stable, right? So now if you look at this axial group over here, which is going up, right? And it's up, down, up, down, up. This carbon here will have an axial bond going up as well. And it could be bonded to a hydrogen or some other group. In this case, it's bonded to a hydrogen, right? because they're facing in the same direction, axial going up, they're gonna bump into each other. They're gonna touch each other, right? And this symbol here means steric hindrance, right? Which means that the two groups here, this isopropyl group and this hydrogen here group, is gonna bump into each other, touch each other, causing steric hindrance. And the steric hindrance is very bad. Like, it decreases stability, right? Because the reason why it's bad is because there's electrons in these bonds, and electrons don't want to be near each other because they are going to repel each other, right? Like charges repel each other. Whereas if you look at the bulky group here in the equatorial position, it's facing away. Like, it's facing away, far away from the other groups as much as possible. So that's why it's gonna decrease steric hindrance. It's not gonna have as much steric hindrance right there, right? And that specific steric hindrance that I just showed you is going to be called 1,3-diaxial strain, which is a specific type of steric hindrance, right? Gauche is another specific type of steric hindrance, but that's for Newman projections, right? Where the two bulkiest groups are going to be near each other, touching each other. In this case, it's called 1,3-diaxial strain because the distance between the groups touching each other they have a 1,3 relationship like that. And diaxial meaning that there's two axial groups having steric hindrance like that. Okay, so be careful because the question could ask you what's the more stable molecule or what's the more like energetic molecule, like which one has more energy, and then your answer would be different. So which one would be more stable, A or B? Which one would be more stable?
A,
right, because the bulkiest group is on the equatorial position, so that's another shortcut that you can think about. The more stable molecule would have the bulkiest group on the equatorial position, right? Like that's the quick way to get the answer. Which one would have the higher energy, A or B? B, right, because B is less stable, meaning that it's going to have higher energy, and that's because the bulkiest group is on the axial position, causing 1,3-diaxial strain. I
actually had a question regarding this. It's on the like annotated problems. Like I thought I had that logic down. It's question number 6 on chapter 4 on the MCQs.
Yeah. Let me see. Question number 6. Yeah. Which would be the most stable conformation of trans 1-methyl 3-isopropyl cyclohexane?
Oh, okay, wait. I think it's because it's trans, but my original answer was C. Because I was like, oh, okay, everyone is on equatorial position, most stable, therefore answer has to be C.
Yeah, that would be right. Like C, like compared to all of the other answer choices, would be the most stable because every single group is equatorial, avoiding 1,3-diaxial strain, avoiding steric hindrance. That would be the most stable, but that isn't trans.
Yeah.
Yeah, right. So that was a little tricky one because of the nomenclature there.
Yeah. So then I was kind of stuck there, and I was like, okay, well, it can't be in the boat, so it can't be D. At least one of them has to be on an equatorial position.
Correct.
So I think that kind of leaves us with it leaves. Oh no, A is
trans.
Oh no, it is trans. Okay,
right. The things that are not trans are B because they're both facing up.
Yeah.
C, they're both facing down.
And
D,
C.
we ignore that. Yeah, C, because they're both facing down.
So
D
the answer is between A and E.
Between A and E, correct. Those are the two real confirmations of the nomenclature that they gave us. Right. And then based on that, the answer would be E because...
Oh, is it because the most bulkiest group is on the equatorial position?
Yes.
Oh, I see. Okay.
Most bulky group is on the equatorial position because that would avoid steric hindrance, avoid 1,3-diaxial strain. Right. So that question had another component to it, which is the nomenclature.
Oh, I see.
Right?
Yeah.
You were just thinking about like comparing all of the chart confirmations, like as it is, as drawn, which would be correct and it would be C because everything is equatorial there,
Mhm.
right? But he made it more tricky by saying the type like of molecule, which is trans, right?
And then D is not right. Like we knew right away because it's the boat conformation, and that's
Mhm.
the most unstable.
Yeah, that bold conformation is the transition state. Like it won't have the preferred angle of 109.5.
Okay.
It's gonna have a lot of strain there, right?
Okay.
Nice. Okay.
I have a couple like I have like 5 more questions that I really need to clarify in chapter 3.
Yeah, chapter 3.
But we can like jump to that at another point if we're still working on chair conformations.
Yeah. I think that's all there is for chair conformation. So it's about axial, equatorial, more stable conformer, less stable conformer, 1,3 diaxial strain. For the there is something about like decalines, right? Let me pull that up. Chapter 4. No. Yeah, decalines. Which is a like a fused ring. Let me see here. Right here. Yeah. Okay. Yeah. So if we have like 2 cyclohexane groups fused together like that, and we look at this carbon and this carbon, and then we look at the hydrogens or whatever group is attached to them. Like let's say this blue one is a wedge hydrogen going up, and then the yellow carbon has a dash hydrogen going down. Would that be cis or trans? Well,
Trans?
yeah, trans. Yeah, shoot. The decalant in substructure is found in many. Yeah. So it's yeah. I thought it was trans too because they're opposite from each other, but on the annotated notes, it said it's cis. Hold on.
Oh, is it because of the way it's connected? Like, because I know it's like the chair conformers. If it's like that, then it was like cis, and then if it was like trans, I think it was like that. Like the 2 chair conformers were like sandwiched.
Sandwich.
Yeah. Let me double
Oh.
check my notes.
Right. Yeah. Okay.
Yeah. So if the 2 chair conformers are like one is like this way and one is like kind of like this way, giving shape, it says it's cis decaline. And then if the 2 chair conformers are like side by side, then it says it's trans decaline.
Oh. So if it's like this, and then are these gonna be the hydrogens we're referring to? That yellow hydrogen and this blue hydrogen right there?
I don't think it's regarding the hydrogens. I think it's just regarding the molecule itself, like
the molecule itself.
Yeah, like the hexane. The
Oh.
cyclohexane.
Oh, right. And this would be trans like that?
Yeah.
Okay. Good to know. Right. That's good to know. Right, because like these are the fused cyclohexanes like that. If it's like this would be the cis decaline, and then if it's side to side, it would be trans like that. Oh, and that kind of makes sense because like if this bond line is side to side like that, the chair conformations would also be side to side like that as well. And then if the cis cyclohexanes are in this shape right there, like one is on top of the other, it would be similar in chair conformations like that as well. Okay, so that's the other thing about decalines, right? Which is good to know for multiple choice questions. Okay. Okay. So now, what are the 5 questions you had, Ashna?
It was from the annotated worksheet for chapter 3.
Yeah.
I mean, sorry, just like the MCQs. So some of the I saw the answers and I still wasn't getting why those were the answers. It was the first one was 13.
13. Which of the following is true for an early transition state?
Like I didn't understand what they were asking me, so I just guessed and I got it wrong.
Right. So this is gonna talk about the mechanism of like free radical halogenation or like any reaction, like really, right? Um, so for this right here, a graph that could really help you like visualize what it's asking you is this right here. So let's say this is the y-axis, which would represent energy, right? E.
Mm-hmm.
And then the x-axis would represent the reaction coordinate or time, right? The time it takes the reaction to complete from converting the reactants to the product, right? Let's say this right here is the starting point with the reactants. Like you have no reaction, just some molecules floating in the solution right there, right? Now the transition state. Do you remember what a transition state means from Gen Chem?
Like the time it takes for it to reach its activation energy.
Yep. And its activation energy is like the peak.
Yeah.
Right? So this is going to be like the transition state, the time it needs to reach its activation energy. And once it gets there, if this is an exothermic reaction, right, the products would be lower energy than the reactants. Like that. Meaning the product is going to be more stable than the reactant because it has lower energy. Right? If the transition state is early, right, then that means that, do you think it's going to be closer to the reactant or product if the transition state is early? Like meaning that it's like it's going to happen soon in the reaction coordinate, like early, like this, and late
to the reactants.
Yep, it would be closer to the reactants. So we can consider this like early, and I will draw you an example of a late one. A late transition state.
So would that just mean it has like super high activation, or that doesn't matter?
Yeah, it doesn't matter. They could have the same activation energy, but early transition state it would mean that it's gonna be closer to the reactants, meaning that whatever is in the reaction coordinate, the molecule would look more similar to the reactants than it would to the product.
Oh, I see. Okay.
Right. Yeah.
Okay. So then the answer should be C. The transition state resembles the reactants.
Yes. Okay. Correct.
The next question I had was question 31.
31.
So my original answer was 3.
3.
And I was pretty confident there, and then it just wasn't that, and I was like, "Ooh, how do I approach this problem more accurately?"
Right. So this one here, just by looking at it, I'm getting confused because it's not in bond line structure, right?
Yeah.
It's in like Kikuli structure. So what I would first do is I would first convert that Kikuli structure into bond line form to help me visualize this. And instead of doing that, I'll just do this right here. Okay, so CH3, CH3, C. This is the CH, this is the CH2, C, and the CH3 is right there with CO2 and light. So now they're asking how many constitutional isomers can be formed from the monochlorination. So we're adding one chlorine to this structure. And constitutional isomers would mean that we have the same chemical formula, but different connectivity. Right. Now, where did you get 3 from, Ashna? I want to see where you got the 3 first.
Okay, so my mind first went to I didn't convert it to the bond line, so I was thinking the two if you put the chlorines on the two ends, that's the same structure.
Correct. So this would be one unique product right there, like that.
Yeah. And then if you move it like one on the inside, that should be the same structure. Like one step inside.
Like this right here? Or this one here.
Yeah.
Yeah, this one, this one here. Yep. That's another one.
Like on both ends, like it should be the same.
Oh, you can't
No.
add one here.
Oh, right. Yeah.
Right, because there's no hydrogen set to replace. Like it already
Yeah.
has the octet row. Like if you added a chlorine there, that would have 5 bonds like that.
Yeah.
Right. Mm-hmm.
And then the last one was like the one in the middle.
Oh, okay. Yep, that would be another one.
So those was where I got my 3.
You're 3. Yes. So
Yeah.
1, 2, 3. There's one more here, and that would be from adding it to any of these methyl groups. Like it could be like that. But if you added it from here or here, it would be the same thing.
Oh, okay.
Right. And that's because, like, you know how this right here, this bond right here, is a sigma bond or a single bond
Yeah.
that has free rotation. If you rotate that, these 3 methyl groups right here can rotate into each other's spots. It's orbiting around. Right. So that's why if you put any chlorine on any of those, that would be the same thing.
Yeah. But then like another question here, we know chlorine likes secondary. So over here, are we like trying to prioritize chlorine getting secondary?
Yes. So if this was the product, the secondary, the product here would most likely be the
That's the
major
major.
one.
Oh,
Yeah.
I see. Okay.
But these are the possible ones as well. But this would be major. Right.
Okay.
And to make sure, we would do the math, like with the selectivity factor chart and stuff like that. But generally, chlorine likes secondary, fluorine likes primary, and bromine likes tertiary.
Okay.
Yeah, bromine is the most selective.
Yeah.
Right. Okay.
Okay, and then the next one was question 38 and 39.
38 and 39.
I think this is to do with the chlorine one.
Oh, right.
Yeah, no, this was super funky because I put the chlorine in, I think the secondary, and then the answer was chlorine was like in a tertiary position. So I was just a bit confused here.
Let's see here. Did you put your answer as B?
Yeah, I think so.
I see. Okay.
Yeah, that's exactly what I did.
Yeah, predicted major products. Okay, so now, because there's something like a benzene is involved, the selectivity would be different now, right? Because let's think about it like this. In the free radical mechanism, right? It's part of the name. The mechanism will have a radical. And what does a radical represent?
An unpaired electron.
An unpaired electron, one lone electron. Right.
Yeah.
Correct. One lone unpaired electron. So before the chlorine attaches onto the carbon, that carbon will have a radical. Right. So now, I don't think you've learned about radical stability yet, have you? Like this is the least stable radical, and then like primary radical, and then secondary radical.
Oh yeah, no, we learned it.
Oh, you guys learned about this?
That's
Okay.
chapter 3, yeah.
Yep, hyperconjugation, right?
Yeah.
The more groups around the radical, the more support it has, right? The more stable it is, right? But that's hyperconjugation. It could also be from resonance. So let's say we have a double bond right there, and we have a radical right here. This radical can do resonance with this double bond like this. Right. Okay. And resonance is a more powerful factor than hyperconjugation. So resonance would be like, if a radical can do resonance, it's the most stable.
Yeah.
Right. So we're automatically gonna ignore this carbon and this carbon, and any of these carbons here in the benzene ring, because those, and this one as well, because, and this one, right? Because they can't do resonance at all. Right. This carbon here that I'm circling and this carbon here that I'm circling can do resonance with the benzene ring. Right, because it's right next to the benzene ring.
Like, you mean the bond, like the double bond flips and goes into the ring, or?
Yeah, like let's say we had a radical here on the top.
Yeah.
If we do those arrows right there, we would have a double bond here and then a radical there. And then this radical can do resonance with this double bond and create another radical here. And then the radical can go, no, not there, but here. like that, right?
Yeah.
So if we draw like the movement of one electron, it's a single hook arrow like that, right? If the radical was over here, this is an sp3 roadblock. It's blocking resonance. We can't do resonance right there, right? Same as over here, right? If the radical is over here, we can't do resonance because this carbon here is already double bonded. The thing that's going to do resonance is the double bond, not the radical.
Yeah. Yeah.
Okay. Okay. So now we're going to focus on this and this and compare the stability between this radical and this radical. We know both can do resonance, so it's going to be automatically the more stable radicals compared to the other ones. But which one is more hyperconjugated? Which one is more surrounded by hydrocarbon R groups?
The top one.
Yep. And that's where the chlorine would be at to get the major product. Right?
Oh, wow. Okay.
If resonance wasn't a factor, then you would do the normal predictions that we have been doing with the calculations.
Okay. So basically, like, if you see that a structure has resonance, what's your like your first thought process? Like, where should you go?
If a structure has resonance, like double bonds or benzenes, then I would automatically look at the carbons next to it that can do resonance, right? Which is like I automatically looked at this one, and I ignored everything else because I know everything else cannot do resonance.
Yeah.
With that thing, like double bond or benzene.
Yeah.
Right. And then from there, because these two have the same amount of resonance, then I look at hyperconjugation.
Yeah.
Which one is more surrounded?
Resonance. Okay, that makes sense.
Yeah.
I think question 39 is basically the same concept.
Yep. Question 39 is the same concept because let's do the same thing. What would you do first to determine the major product if we have this benzene, which we know can do resonance?
Okay, so I would look to the carbons next to the resonance ring who can like take on the double bond. So it's that, those two that you've highlighted. And the one that has more hyperconjugation is the one with the methyl. So therefore, like, chlorine has to go there.
Yes. Nice. Nice.
Okay.
Okay. Like that. Okay.
There. Okay. Yeah, that makes sense. I think I have the last. The last one is 48.
48. Which radical is the most stable? Okay. What answer did you get? I'll draw out the structure.
I've got A.
Oh, A. Oh, is that what you got like as your answer?
Oh yeah, that's what I've highlighted. Is that the right one?
Yeah, that's the right one.
Oh, maybe I corrected my answer then.
Yeah.
Yeah.
Yeah. I think were you confused about like this like this is the more stable radical, but some people might have thought it was this.
Oh, I think that's probably what I'd done.
Right. This right here, like if I drew out that radical right there.
Yeah. Or maybe I thought it's C.
C. Oh, that one.
Yeah.
Right there. Yeah, I see. So let's compare all of those. Like this one, and this one. Okay. So this radical here is going to be called a tertiary radical, right? I'm not going to say radical because it's going to be the same for all of this. So this right here is a tertiary radical. This one right here, if the radical is on a carbon that is like double bonded, we call that vinylic or vinylic position. Right. Before we go over that, let me show you the difference between vinylic, allylic, and benzylic. Right. So let's say we have a double bond right there. If a radical is right there, that's vinylic position. If we have a radical right here, that's allylic position, which is like one carbon away from a double bond. If we have a benzene and the radical is right there, that's phenylic. If we have a benzene here and another R group coming out of the benzene ring, like let's say this ethyl, and we have a radical right next to the benzene ring, this is benzylic.
Okay, wait, let me just take a screenshot of that.
And then allylic and benzylic, the ones that I highlighted,
yeah,
they can do resonance. Resonance. Whereas vinylic and phenylic, those radicals or carbon cations, they could be carbon cations or anions, they cannot do resonance because it's on a carbon that is double bonded already, and that double bond is gonna like prevent the resonance from happening. Okay, so now if we look back to here, this is phenylic.
Yes.
Right, because it's on a benzene.
And so it cannot do resonance.
It cannot do resonance, right?
Oh.
Whereas this one here is a secondary benzylic. And can that do resonance if it's benzylic?
Yes.
It is. So it will automatically be the more stable one because of benzylic. Like, even though it's secondary, which is less hyperconjugated than tertiary, it has this benzylic part to it, which can do resonance with the benzene, making this more stable than the tertiary one, right? This is a tertiary phenylic, right? Phenylic cannot do resonance. So that's why this is less stable than this secondary benzylic. The secondary benzylic is more stable.
Like option C and option E and D is basically the same thing, right?
Yeah, they're all phenylic, right? They're all basically the same thing, correct?
And then B is definitely not because it's like, it's a methyl.
It's a primary radical.
Oh, it's a primary radical, so it's like the least unstable. And then A is a secondary radical.
Yes,
So
secondary benzylic radical. Benzylic is the one that makes it like more stable, right? It's like right next to the benzene ring, right?
Okay.
Nice.
Okay, yeah, I think that is all the questions I had for chapter 3. That was the one where I struggled the most.
Chapter 3, the one with the free radical halogenation.
Yeah, that like chapter 3 was like, I found the MCQs there for like really tricky. I got like a lot wrong. But I think it's a lot more clear now.
That's good because there's a lot of conceptual stuff like this. Like if you don't see it visually, then it's hard to understand it. And, and understanding the concepts like resonance, hyperconjugation as well. Like those things, like those little things add up to chapter 23, which is why it makes it difficult.
Yeah. Wait, why can't vinylic do resonance?
Vinylic can't do resonance because it's on a carbon that is already double bonded.
Oh, okay.
Right, and this double bond here is occupying the empty p orbital, which makes the radical in an sp2 orbital, making it localized, stuck there.
Okay.
Right? But because this carbon here is next to the double bond with p orbitals, this radical here can hop onto those p orbitals and do resonance with them.
Okay.
Yeah.
Okay. Yeah. Well, that's all the clarifications from my end. Yeah.
Yep. I'm glad that helped.
Thank you so much, Brian.
Of course, Ashna. Good luck on the midterm tomorrow.
Thank you.
Yeah.
I'm ready to hop off. So I just want to say thanks to everyone and I wish you guys all the best.
Yes.
All the best, Amanda. Thanks for all your help, Brian.
Yep, of course. Good luck and let me know how it goes tomorrow.
Sure. Okay.
Good luck,
all right.
Good luck.
Bye.
Bye.